Okay, hello. So we're back from our Christmas break a bit belatedly. And we're going to do something a little bit different with the video this week in that we're going to be talking through a paper. It's a rather interesting paper because it deals with some interesting sort of problems in high-performance computing and where it's going to go. And it's a fairly light-hearted, easy-to-read paper and deliberately designed to be. And I could heartily recommend the paper, and I'll put the link for the paper and another website that I'm going to show in the description for this video. And this is a news article about the paper we're going to talk about, and the paper is called Myths and Legends in HPC. Now, the with some legends bit in the title on this website, and I'll put the link to this in there as well, is because there is an interview with the authors of the paper here, which is also very interesting and well worth listening to. So what I'm going to be doing here is I'm going to briefly go through the myths that they describe in their paper and sort of give a combination of a overview and my opinion, our opinion, on what they're talking about and how it plays into things. Now, I should say why we're doing this, and the reason is because one of the things that always crops up in high-performance computing at the moment when you talk about it is a question of where is it going to go, what's it going to do, what's it going to be like in the future. And, you know, if you develop something for high-performance computing now, are you designing something that is going to be a dead end? Is it going to be useless? Is it going to be ready for the future? Or things like that. And this paper actually neatly addresses some of those questions about where it's going to go. So move across the actual paper. This is the version of it on arXiv, but as far as I know, this has actually been published on arXiv. It's not on arXiv pending publication in a peer-reviewed conventional journal. It's been published on arXiv. So obviously they go through the introduction, but I'm not going to particularly talk through that. I'm going to go through their myths section. So here's the first one: quantum computing will take over HPC. Now, their argument here is pretty much that quantum computing doesn't necessarily map very well onto all of the sort of problems that are being used in current high-performance computing. And I think that is very much true. As they point out in the paper, unstructured data mapping onto a quantum state isn't very easy. And quite often you're left with a situation where a lot of time has to be taken to set up the quantum states, and you can use that quantum state to answer one problem, but you then have to set it up again to answer a slight variation on the problem because the nature of getting the answer out of your quantum state destroys the quantum state. And I think the other thing that they don't particularly mention here is that, as it stands at the moment, quantum computing is not advancing quite as fast, I think, as people hoped it would. Quantum computers are moving along. They're definitely becoming a thing. You can start getting access to them. But as it stands at the moment, you know, experts talking about quantum computing say that, you know, conventional cryptographic algorithms, which are one of the things that can be very easily attacked with quantum computers, are probably safe for years, decades. Not, you know, quantum computers are not going to come along and start solving even well-suited problems in the next couple of years. So I don't think one has to worry too much about quantum computing taking over HPC soon. And they ask the question, when will it be commercially profitable? What will be the first useful algorithm? And what will be a breakthrough enabled by a new quantum algorithm? So their second myth is here, and it's everything will be deep learning. So the idea of this is that essentially you can use machine learning to solve problems in sort of the classical areas of high-performance computing: computational physics, computational chemistry, computational biology, those sort of problems. The idea being that you train your machine learning system based on conventional simulations, and then you don't have to do conventional simulations to get the answers for other problems in the area. You can just use the trained machine learning system and it will tell you the answer. And, well, as they point out here, essentially the problem with that is that machine learning type approaches mostly just they learn patterns. You know, if the space of the solutions of a problem is nice and smooth and doesn't have any unexpected structure in it, machine learning will learn that space and it'll give you back an answer quite well. But in areas where there are rapid changes, in areas where there are discontinuities, in areas just where things don't behave quite the way you would expect, machine learning is more likely to make mistakes there. And I would say that in an awful lot of areas of research, those sort of places are exactly where your interesting results live as well. So I think there is a very definite thing that machine learning definitely has a place. In particular, it is usually substantially faster than classical simulations. So if you're in a situation where all you want to do is try and find interesting areas of a theoretically fairly smooth parameter space, machine learning can be a nice, quick and easy way of getting you there. But I don't think myself, this isn't particularly what they say it is unclear, but I don't think that you'll be able to completely replace conventional, what they term first principles simulations with machine learning type systems. And their questions on this are, will machine learning be able to replace or just augment? Where will they fail to deliver? And how can you classify what can be accelerated by machine learning and not? And those are definitely good questions. Okay, so myth 3. Extreme specialization is seen in smartphones or push supercomputers beyond Moore's law. So the idea of this one is that essentially you can use more specialized hardware intended for solving specific problems to solve those specific problems faster than if you just used a computer and relied on that computer to get better. If you're not familiar with Moore's law, it was a statement made many decades ago that broadly every 18 months the number of transistors you can fit on a computer chip doubles. And that's mostly kept up to the modern day. And to a degree, at least for a lot of its history, it was a good proxy for how fast computers were. That proxy is broken down almost completely. And nowadays, what you pretty much have is much more, it's a proxy for the number of cores a computer has. Not so much how fast each individual core is, but it's still more or less going on. So the question is, to what degree can you build specialized systems that are faster? And the answer is undoubtedly you can. So the use of graphics cards for solving computational problems is an example of this succeeding. And as they point out in this paper, a great degree of the success of GPUs is because GPUs have very high memory bandwidth. As I say here, primary reason for success is high memory bandwidth, a feature known since the vector supercomputer days, which is now adopted by mainstream CPUs such as the A64FX and Intel Sapphire Rapids. So I'll just switch across. This is a slide that Intel gave at Supercomputing 22, a conference last year, which describes basically how performance of computer cores versus performance of memory has changed over time. So this is not actually a very good picture, but it was the best one I could find. And it basically shows that from 2013 to 2021, you had an increase from about 40 high-performance LinPack marks per core up to about 120, so call it a factor 3. But there's been a tiny change in the read-write bandwidth per core of memory for the computers over the same time. So essentially, you can do more compute, but you can't get more data into the processors for them to do that work. And that is very important because an awful lot of computational problems, particularly in science, but in other areas of academia as well, is dependent on doing not tremendous amounts of work on fairly large amounts of data. So that's a sort of thing where something like a GPU comes in. It has many cores, but they're weaker and very high bandwidth memory. So GPUs work quite well on that. Now, they do mention the A64FX and Intel Sapphire Rapids. A64FX is a little niche, but Sapphire Rapids has now been released since this paper was written and is now the new Intel Xeon Scalable line. And in particular, there's one version of it which is called Intel Xeon Max, which has what's called high bandwidth memory. So this is an attempt by Intel, who are making CPUs, to push higher memory bandwidth into conventional CPUs. Now, the question then comes, other than GPUs, are there other elements, are there other things you can put in to solve problems that will speed things up? Now, I'm not going to go through their argument here. It's one of the longest ones. But essentially, they come to the conclusion that probably not. So, for example, the example of smartphones, which really have become more and more powerful over time, a large chunk of the advantage of the cost of a smartphone is not actually the bit that does the work. It isn't the processor, it's the phone, it's a screen, it's the storage, it's the battery life and things like that. So as a consequence, you can afford processors to get more expensive in a mobile phone, and that's a chunk of what's happened there. They also sort of make the point that unless it's extremely easy to use all these accelerators that people are potentially talking about, getting programmers to adopt those models isn't easy. Now, I'll say in one of the later myths that there are various programming models that are designed to make things like this easy, but you can't make it actually easy simply because what people want to do is so different, and the entire reason for using these accelerators is to get higher performance. So you can't write something that's generally applicable but not performant. You have to write something that's generally applicable but allows enough customization that someone can optimize it for their particular problem. And that generally means that it has to be harder to use. So to a great degree, I think the takeaway here is, again, what they say in their questions. So will heterogeneity happen, i.e. will you start seeing high-performance computing with lots of different accelerators? I don't really think so, because of the fact that most of the things that are coming around now as possible accelerators have been around for a long time. One of the things that people keep talking about, which will come back in one of the later myths, is what's called a field programmable gate array, and those have been around since the 80s, and they've always been the next big thing, and they never really have been. And maybe I'm wrong, and this time they will. But I don't think so. Second of all, are supercomputer workloads worth extreme specialization? In some senses, yes. They use a lot of power, they use a lot of time, they use a lot of resources, so anything you can do to speed them up is good. But in reality, one of the key elements of academic programming is that time to solution in total is generally the key. So developer time is very important as well, and developer availability is also a major bottleneck. So people like us, research software engineers, are in part to solve that availability problem, but there still aren't enough for us to be spending all our time doing things like writing specialized libraries for high-performance computing. And yeah, when will we have production supercomputers with more than one accelerator type? The one accelerator type we do have is GPUs. I think it'll be quite a long while. So the next myth they go through is related, which is everything will run on some kind of accelerator. So essentially, the idea here is that the CPU is not going to be the major thing that does the work in future. It's going to be accelerators. It's going to be GPUs, these FPGAs, field programmable gate arrays. And and those are going to be the things that do the work in future. Well, it's possible. I think you can make, as they sort of do here, an argument that there's a sort of historical element. Special purpose vector machines that had to be carefully programmed dominated scientific computing in the 70s and the 80s. But as soon as normal computers came along that you could program much less cleverly, the ease of programming meant that they massively took off. And the fact that people write stuff for GPUs, which is harder than writing the same things for CPUs, although usually not that much harder, partly due to a well-designed interface, but also partly due to the fact they're not that different in a lot of senses, means that people will make some effort. But I think it's debatable the amount of effort people will put into changing it. But equally, not all problems map terribly well onto GPUs. At the moment, part of the problem with it is that GPUs are not entirely balanced for all. Well, CPUs aren't entirely balanced for every problem. That's why GPUs work better for things. But there are just some types of problems that are real and exist in scientific computing where you can put in a lot of effort to move something to a GPU and you'll get maybe a doubling of performance or maybe no performance improvement at all. An awful lot of the stuff where 100-fold improvements from moving to accelerators was possible have mostly already been changed and are happily running on GPUs. Most of what's left are things that do not map on very well. So that does bring us to these field programmable gate arrays. So the idea of a field programmable gate array is it is a chip where you can directly modify the circuitry inside it, effectively. So if there is a certain part of your algorithm that can be represented in Boolean algebra, say, very well, then you can use one of these field programmable gate arrays and they can do that job faster than a general purpose CPU, because effectively once they've been programmed with your solution to your problem, they are faster than a CPU trying to do it using generic circuitry. The problem with that we'll come to in the next myth because it mentions it a bit more. But they ask very good questions, which is, will CPUs become pure servants to accelerators? Maybe, but I suspect not. The difference in performance is quite often not remarkable except for certain workloads that work really well on GPUs. Are accelerators actually more than just better balanced processors? I would argue no. That is essentially why you have this real difference of how much faster you can get on a GPU than a CPU. For some things, GPUs are just so much... Well, accelerators in general can be better balanced, but GPUs are by far the most common at the moment. And they are just better balanced for certain types of problem. Will reconfigurable accelerators see a renaissance? The answer to that, I think, is possibly, but even more so than things like GPU programming and accelerators in general, I think these reconfigurable accelerators, these FPGAs and the like, are going to be dependent on a good programming interface for ordinary programmers. To get the full power from something like an FPGA, you cannot write your program in C or C++ or Fortran or Python. There are special languages for writing things on these FPGAs. And it is not an easy way to think. It is only worth it if you get tremendous speed-ups. And so that's where myth 5 comes in here. Reconfigurable hardware will give you 100-fold speed up. And ultimately, this is, again, it's been promised forever. And FPGAs are tremendously important. There are jobs they do where they are brilliant. But they give here A very important quote. Without offering at least a factor of 10 times performance gain at moderate porting costs, FPGAs are not a factor in our current planning because of their unprogrammability. So FPGAs are brilliant if you have one job that you want to do and you want to keep doing that job again and again and again, but not enough to have an actual custom chip made. Because there is a lot of work in writing them, at the moment at least, and the performance gains are not always brilliant. I mean, for example, one of the things you can always do if you have some piece of code that's running on a CPU is you could use a large enough FPGA to produce a CPU and run your code on that. But it won't be faster than the actual CPU. It'll be slower. In fact, people do that sort of thing very much in the retro computing enthusiasts area, people who try and keep old 1970s, 1980s computers alive. They use field programmable gate arrays to reproduce no longer available old processors that you can just plug into the sockets on an old computer, and it will emulate those old processors. It works, and a modern FPGA is as fast as a 1970s processor, but it's not as fast as a modern processor. So the value of FPGAs is not in them being FPGAs, it's in you being able to create specific hardware for solving your problem. And that's the difficulty. So, they don't particularly say much, although they do mention another thing which is called coarse-grained reconfigurable arrays, which are they have bigger units on them. You're not just reconfiguring basic logic gates, you have more complicated things that are wired up in different ways. They could be a game changer. They're still new enough that I don't think anybody knows. And again, their questions here are important. Will the HPC community embrace FPGAs as alternatives to GPUs in large-scale production systems? I think not, unless a better programming model comes about. Can the community afford a fool me twice moment? Well, there have been lots of things over the years where there have been promises of amazing performance improvements that haven't been realized, and FPGAs have been there pretty much every time. I don't think they're going to win this time either. So CGRAs, these configurable, coarse-grained reconfigurable arrays, will they take the place of FPGAs? Maybe. They have potential in quite a few things. I don't know at the moment. So myth 6 I'm going to skip over. That is, we're going to be at Zeta scale soon. That's about energy efficiency and performance improvements over time. And this graph is somewhat interesting. Efficiency in gigaflops per watt is going up massively. Computers may be drawing more power than they ever have before, but they're also being much more efficient than they ever have before. Okay, next generation systems need more memory per core. I'm going to partly skip over this one because it's not particularly interesting, but one of the things that has changed is as we've been getting this more and more compute power, everyone's been saying, okay, we don't want more compute power, we want more memory. We want more memory capacity, we want more memory bandwidth. In particular, we want more bandwidth so we can get more data into the CPU. And essentially their argument here is, well, yes, that's true as it stands at the moment for an awful lot of HPC type workloads. Processors have too much compute for the amount of data you can get into them. You analyze an awful lot of scientific codes in particular, they are unable to work at the full potential performance of the processor because the data simply cannot be got into the processor fast enough. But essentially the thing in their question that is really important is, and here's the right one, that's what I skipped over, what will be the next bottleneck resource? And that one's important. You fix the memory problem, there'll be something else. What will it be? We don't know. At the moment, I think that's something important. That, we, and their third point here, we need to adopt a performance modeling discipline to discuss bottlenecks scientifically. There are people working on that. There are people at Warwick in computer science whose entire research is on modeling of computer performance, and it's a very big area. But it's not used in anger much in the high-performance computing world, and maybe it should be. Okay, myth 8, I'm not really going to talk about because that's about details of how you put things in a data center. The idea that rather than having a network of lots of computers that are complete processors, memory, potentially hard drives, and networking them together, you can instead disaggregate it. So you have processors in one place, memory in another place, and they talk over interconnects. And there are technical reasons why that's quite difficult, but that's quite specific. So myth 9, applications continue to improve even on stagnating hardware. So this one's partly a myth, I think. But there's a graph here essentially showing, so this line here is that Moore's law, which is effectively performance doubling every 18 months. And it goes to show that in various areas of science, these ones are actually amusingly from the area I used to be in of plasma physics, that you can jump above Moore's law periodically by coming up with better algorithms, essentially, in almost all of these. So, here, is delta F, which is essentially a way of representing only the changes to something rather than the whole thing, which is more efficient. Here on combustion kinetics, you have adaptive mesh refinement and higher order adaptive mesh refinement and things like that. But overall, that sort of thing is important, but, well, the main points they put here in the answer are really important. As the performance improvements from hardware technologies drop, should we increase investment in software? I.e., given that we are now in a world where what we're getting more of, more compute, we can't use because of that memory bandwidth problem, do we need to up our investment in software? As a software developer, I think in some senses the answer is definitely yes. You certainly need to have a much more of a concentration on making sure the software you're developing is developed well. But on the other hand, this point 3 is a very important one. To what degree are we willing to refactor or rewrite legacy code bases when or if hardware stagnates? It already, in a sense, has stagnated for a lot of things. You can get by throwing bigger computers at it, bigger supercomputers with more individual computers in it, but computer performance improvements are not anything like they were for scientific code just from each new generation of computer coming out. I think there's also another point that they are missing there is as you optimize more closely for one given design of hardware, you are becoming less and less able to exploit advantages in other hardware when it becomes available. And I think that is a problem as well. Okay, myth 10, Fortran is dead, long live the DSL. So I will put my cards on the table here. I like Fortran. I think it is a good language for particularly scientific computing. And they actually make that point in here. It is well designed for the purpose of expressing mathematical programs at highest performance. And it is difficult to... No, I will phrase that more carefully. It is easy to write code in another language, like C or C++, that is less performant than the same code written in Fortran, often while spending more effort writing the code in the other language. Fortran is actually quite good at what it does. So I think that Fortran is not as well a language in terms of use as it used to be, but I don't think it's going anywhere immediately, and I think it has potential in the future. I think the advantages that Fortran has are still very real. Okay, so domain-specific languages. Now this is a bit of a vexed question, and they don't really have an answer here. The point of a domain-specific language, or DSL as they say here, is you do not try and write your code directly in a language like C or C++ or Fortran. You write it in a domain-specific language that is optimized for the type of problem that you're working on. And what you mean by type of problem that you're working on could vary between something that's intended for problems involving just simulating particles at one end, not very specific at all the way to a language intended for solving the problems of global MHD simulations in a tokamak. which is very specific indeed. But they make a couple of good points here. So any language becomes more complex over time. Fortran 66 evolved into the complex Fortran 2018 language standard. I will tell you for a fact that Fortran 66, while it has massive downsides as a language, is far easier to program in many senses than Fortran 2018. And if you wanted to write a program to use all of Fortran 2018, it would almost be impossible, whereas writing a program that used every element of Fortran 66 would be fairly trivial. So are DSLs subject to the same problem? They'll keep widening? Well, possibly, because if they do, they're just going to be a general purpose language again. And the other point that they make is that at the low level point, you have people who are perfectly happy to dig down and actually deal with stuff fairly close to the hardware. So I think that is a fair point. DSLs undoubtedly have their place, simply because they allow somebody without deep experience of programming at the low level to write problems at the high level. Where they're going to sit, I don't know, and whether they're going to replace codes written in traditional languages, I don't know. I suspect the answer is probably not, simply because a DSL that's general enough to still allow people to solve the problems that they want to solve would also have to be generic enough that it's effectively just another programming language. Okay, myth 11. I'll go through this one again fairly quickly because it's a bit niche. So HPC will pivot to low or mixed precision. So most high-performance computing is done using what's called FP64, so floating point numbers represented using 64 bits of memory for each number. One of the key things that allows machine learning systems to run so fast is that they often do not generally, in fact, almost never need to run at this 64-bit precision in order to get useful answers. So as a general rule, they are done using smaller numbers. Now, it's not immediately obvious why, but most processors can process smaller numbers faster. So, for example, in pretty much every processor, in the time it takes your processor to add together two 64-bit numbers, it could have added together four 32-bit numbers. Some processors, notably GPUs, could even extend that to 8 16-bit floating point numbers. So, in theory, you have a huge potential advantage in performance by not just blindly using 64-bit precision. And certainly not blindly using 64-bit precision is something that people do. They think about what precision they need. So the question here is much more, can you go away from 64-bit precision in areas that look like they need it? And the answer to that is usually yes, by changing your algorithm in some ways. But they make the point here that effectively, at least in some cases, you would require domain experts in HPC to study the numerical stability of solvers to identify, on a case-by-case basis, the susceptibility of solvers to lower mixed precision. So they go through other automated things, but ultimately, for a lot of problems, someone would actually have to sit down and carefully work through the algorithms, pen and paper. This isn't a programming problem, this is a numerical analysis problem, and work out, will this algorithm still work at lower precision? And I don't particularly think that, unless we're in a world where there's also a lot of other effort being expended on programming, which there might be, I don't think this is going to be a big part of HPC in future. It might happen, but I don't think it can be made very easily into libraries, so it's automatic. I don't think compilers can do it automatically very easily. And I don't think a huge amount of effort is going to be spent by the HPC community doing it manually. Okay, so this one, myth 12, this is in some senses the important one. Because, and this is the one that sort of led me to want to make this video, which is all HPC will be subsumed by the clouds. So the question here is, at the moment, almost all high-performance computing equipment is that people use is either run by a national supercomputing center or a regional supercomputing center or their own institution. And that's true if you're doing high-performance computing, pretty much whether you're working for a company or in a university. So the question comes, given that there now are all these cloud systems about, which are very large, fairly tightly connected computer systems, will supercomputers basically just be something that you purchase in the cloud? So the one thing that they note here has definitely happened is what they term the cloudification of supercomputers, and that has definitely happened. HPC is becoming more and more open to ways of using it that is not logging on over an SSH connection and submitting a Slurm script. On balance, that is a good thing, although given that using HPC is a difficult thing in general, there is a limit to how easy you can make it before essentially you just move what is the limiting feature of making use of the system. But the supercomputification of clouds, as they call it in this paper, is a little bit more unclear. As it stands, if you are using your HPC systems pretty much flat out, which most HPC systems in academia are used like, it is not at present even remotely practical to move over to a cloud-based system. It will be more expensive and it will be harder to administer. However, as they say in this, what will tend to happen is that research and development expenditure in IT will become more and more suited to the kinds of problems that people use clouds for, and they will be designed around cloud-based systems. As they point out, the R&D expenditures of hyperscalers in IT now outclass government investments, and increasingly the hyperscalers are investing in high-end computing. Hyperscalers is a general term for those people who are running cloud and cloud-like infrastructure. So you could, in theory, wind up with a situation where they have developed a system where, for the types of highly specific workloads that the systems are optimized for, the cloud systems are cheaper. I'm not sure that that is going to be true, simply because a large chunk of the cost of operating a cloud-based supercomputer is not the hardware. The hardware is not insignificant, but the humans running the system are important, and those cannot be removed, whatever you do, simply by moving something to the cloud. You still need somebody who's administering the submission systems. You still need somebody who's responsible for deploying the software packages your users want. You still need people like the research software engineering group who help people move their codes over to using these systems and make sure that they can use them properly. And those people will generally not move over to the cloud's side simply because even in a world where HPC moves into the cloud, they are not going to be primarily dealing with those people. So they almost certainly won't have staff who primarily work on that sort of job. So my suspicion is that it is not going to become cheaper in any time soon for HPC to move into the cloud entirely. I think we'll see more and more use of cloud, especially for niche or unusual hardware requirements. But they also make the point here that even if you do get a lot of stuff moving into the cloud, some things probably won't be well met by the cloud, which will probably be met by remaining on-site systems. And their questions are, again, highly relevant. What would be a defining development to decide between cloud and on-premises? Well, a lot of possibilities there. Cost is one. difficulty of getting enough staff to run on-premises systems is actually a thing. Okay, when will more than half the cycles be spent in the cloud? I think that'll be a while yet. And will on-premises systems be niche or remain with a significant fraction of HPC cycles spent? I will be honest, I suspect that for a long time yet, we will be seeing on-premises HPC remaining a thing, even as cloud becomes a bigger fraction of all HPC time used. Okay, so that was a very personally opinionated view of, based off this paper, of HPC, what it looks like and where it's going. I think the key thing to take away from a lot of this is a lot of the people who are predicting the future to be radically different to the present are probably wrong. If you want to start writing a program now in Fortran, there's no reason not to. If you want to write something for a CPU, I don't think in 5 years that investment's going to be wasted because everything's going to be GPU or FPGA. I don't think that designing something around the idea of running it on a cluster at your own university is something that's going to become a wasted investment in 10 years when everybody's moved to the cloud. I think that over the next 10 to 20 years, while things are going to change, and I think a lot of new things are going to come in, I think that anything that you could write now is going to still be useful in 10 years, I suspect in 20 years as well. So I think that's why it's valuable to go through these sort of myths and legends, because it's very easy to assume that, well, I just have to wait for the next big thing. I wait for the DSL. I wait for the next generation accelerators. And there is some very exciting stuff coming up. But I don't think that you have to wait to see what the future is going to bring. I think that while the future may bring amazing things, in fact almost certainly will, anything that you choose to write now is still going to be working in a decade or so. So that finishes this, and hopefully we will be back next week.